Assalamualaikum and hi again. This is the fourth topic under estimation. In this session, we are going to explore the methods of estimating an unknown population parameter denoted by mu1 minus mu2, which is a difference in two population means. Let's go. Before we explore the content of this topic in detail, let us look at the topic learning objectives. At the end of this session, you should be able to achieve the following three objectives. First, you should be able to obtain a point estimate for a difference in two unknown population means denoted by mu1 minus mu2. Second, you should be able to construct a confidence interval for mu1 minus mu2. And finally, you should also be able to interpret the constructed confidence interval from mu1 minus mu2. To start with, let us explore on the point estimate for mu1 minus mu2. Look at this question. What is the point estimate of the difference between two unknown population means mu1 minus mu2? If you have already watched the other videos on estimation chapter, you may anticipate the answer. Yes, the answer is the difference between two sample means calculated or obtained from sample data. Here, x bar 1 is the point estimate for mu1, and likewise x bar 2 is the point estimate for mu2. If you are interested to find the point estimate for mu2 minus mu1, then you can simply use x bar 2 minus x bar 1. Notice that the position must be consistent. In other words, the point estimate for mu1 minus mu2 is x bar 1 minus x bar 2. In reverse, the point estimate for mu2 minus mu1 is simply x bar 2 minus x bar 1. In summary, the point estimate for a difference between two unknown population means is simply the difference between two sample means that we can calculate from sample data. Let us look at the following example on finding a point estimate for mu1 minus mu2. Here, we have Mr. Y who is investigating if there is any difference between the car speeds at 1 km before and after a speed camera located at a particular highway with a 110 km per hour speed limit. He randomly collected the following data. Assume all car speeds at 1 km before and after the speed camera are normally distributed. The question is, find the point estimate of the difference between the unknown population mean speeds at 1 km before and after the speed camera. Now, what do you need to do first when you are given sample data like in this example? As you can see, the sample information such as the values of sample mean and standard deviation are not given directly. In this case, you have to use a scientific calculator to get the sample information from the two sets of sample data recorded before and after the speed camera. Please recall the skill of getting the X-bar value from your scientific calculator. Remember, we have gone through the steps of getting sample information from a set of sample data in Chapter 1 quite some time ago. Now suppose 1 and 2 refers to before and after respectively. Do you get X bar 1 equal to 106.7 kilometers per hour? What about X bar 2? Do you get 115.5 kilometers per hour? If you do, your answers are correct. Remember, X bar 1 is the point estimate for mu1 and X bar 2 is the point estimate for mu2. Having obtained the values of X bar 1 and X bar 2, now you can get the point estimate for the difference between the unknown population mean speeds at 1 kilometer before and after the speed camera given by X bar 1 minus X bar 2 equal to negative 8.8 kilometers per hour. If you have a difference of mean speeds after and before, then the answer is 8.8 kilometers per hour. Any of these answers is possible as the inference you will be making will be the same. What can you say about the point estimate value? A possible inference is that on average there is an increase in the car speeds after passing the speed camera. Do you agree with me? Let's proceed to the next topic. You may want to refer to the textbook Statistics for Engineers pages 67 to 70, which explain this topic with working examples and task questions. Now recall from Chapter 2, we know that the sampling distribution of the difference between two means X bar 1 minus X bar 2 is assumed to follow a normal distribution with mean equal to mu1 minus mu2 and variance equal to sigma 1 squared over n1 plus sigma 2 squared over n2, where sigma 1 squared and sigma 2 squared are the variances from population 1 and population 2 respectively, whereas n1 and n2 are the respective two sample sizes. The standardized random variable for X bar 1 minus X bar 2 is then given by the following expression. Z equals to X bar 1 minus X bar 2 minus the mean of the sampling distribution of the difference between means given by mu1 minus mu2 divided by the standard error of the sampling distribution of the difference between means, which is the standard deviation of X bar 1 minus X bar 2 given by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now let us focus on mu1 minus mu2 and consider this difference between the two population means as our parameter of interest. Rearranging the Z formula, we then have the following expression. mu1 minus mu2 equal to x bar 1 minus x bar 2 minus z multiplied by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. By borrowing this formula, we can now construct the confidence interval for the difference between the unknown population means mu1 minus mu2, which will be explained further in the following slide. From the previous slide, we had rearranged the Z formula into the expression below, where mu1 minus mu2 is x bar 1 minus x bar 2 minus z times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. By borrowing this expression, we now construct a confidence interval for the difference between two unknown population means, mu1 minus mu2. The two-sided 100 times 1 minus alpha % confidence interval for mu1 minus mu2 is then given by x bar 1 minus x bar 2 plus minus sec alpha over 2 times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Notice that the difference between the sample means random variable now becomes the value of the difference between two sample means, which is the difference between the point estimates of mu1 and mu2 given by x bar 1 and x bar 2 respectively. The minus sign now changes to the plus and minus sign as we have a two-sided confidence interval based on Z distribution which is centered at 0. The Z random variable in the above formula now changes to the value of Z at alpha over 2, that is a Z score at alpha over 2. The standard deviation of x bar 1 minus x bar 2 remains the same. That is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 does not change. Now if you look at this expression, which is the product of Z alpha over 2 score and the standard error of x bar 1 minus x bar 2, this is what we call a margin of error. A margin of error. We can find out what the margin of error is in constructing the two-sided 100 times 1 minus alpha % confidence interval for the difference between two unknown population means mu1 minus mu2 by multiplying the Z alpha over 2 score with the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. It is worth noted that what we have here in this slide is case 1, where both population variances sigma 1 squared and sigma 2 squared, or the population standard deviation sigma 1 and sigma 2 are known, regardless of what the sample sizes n1 and n2 are, whether they are large or small. In fact, we have 5 cases altogether in constructing the confidence interval for the difference between two unknown population means. We will explore each of these cases in the following slides. What are the 5 cases we need to observe when constructing the confidence interval for mu1 minus mu2? You already knew the first case from the previous slide, didn't you? Let us recall the first case again. When the values of population variances sigma 1 squared and sigma 2 squared, or the values of the population standard deviation sigma 1 and sigma 2 are both known, then we can use a z-score in the confidence interval formula. That is, the two-sided 100 times 1 minus alpha percent confidence interval for mu1 minus mu2 is x bar 1 minus x bar 2 plus minus z alpha over 2 times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. For this case 1, we do not have any constraint on the sample sizes n1 and n2. These sample sizes can either be large or small. So this is what case 1 is all about. We know the population variances values sigma 1 squared and sigma 2 squared. We do not have to worry about the sample sizes large or small. And we do use Z alpha over 2 score in the formula. So we can regard this case 1 as category 1. What if the population variances sigma 1 squared and sigma 2 squared are unknown? If this happens, then we have the rest of 4 cases to deal with. What are the 4 cases? The 4 cases actually fall under 2 main categories. 2 cases are under category 2 and the other 2 cases are under category 3. That's why I said case 1 would be category 1. So for category 2, both sample sizes N1 and N2 are large, that is, being at least 30. Here under this category, we can still use a Z alpha over 2 score in the confidence interval formula. However, for category 3, either the first sample size N1 or the second sample size N2 is small, or both of the sample sizes N1 and N2 are small, that is, being less than 30. Here we cannot use Z alpha over 2 score anymore. Instead, we change Z alpha over 2 with a T alpha over 2 score with a degrees of freedom nu. So the cases under category 2 are case 2A and case 2B, where in case 2A, we have the assumption on equality of population variances, that is, sigma 1 squared and sigma 2 squared are assumed to be equal. Here, the unknown population variances sigma 1 squared and sigma 2 squared are estimated by a pool or weighted variance denoted by SP squared, which is given by this expression. The formula for SP squared, which is the pool variance, is available in the statistical table and formula booklet page 2. For case 2b, on the other hand, the population variances sigma 1 squared and sigma 2 squared are assumed to be unequal. Here, the sigma 1 squared and sigma 2 squared are estimated by the sample variances S1 squared and S2 squared respectively. In other words, we do not use the pool variance SP squared when we do not have the equality of population variances assumption. Similar to cases 2A and 2B, under category 3, we have cases 3A and 3B based on whether the population variances are assumed to be equal or not. So in case 3A, which is similar to case 2A, we have the assumption on equality of population variances, which requires us to use the pool variance SP squared in the confidence interval formula to estimate the unknown population variances sigma 1 squared and sigma 2 squared. Whereas in case 3b, which is similar to case 2b, the unknown population variances sigma 1 squared and sigma 2 squared are assumed to be unequal. Again, in this case, we estimate the unknown population variances by the sample variances S1 squared and S2 squared respectively. That is, we do not use the pool variance SP squared in case 3b. Now, what do you think the values of the degrees of freedom nu for case 3A and 3B? Are these degrees of freedom nu be the same for both cases, or are they going to be different? Let's find out the answer in the next slide. Before answering the question on what degrees of freedom are for cases 3A and 3B, let's browse through again quickly on cases 2A and 2B. Case 2A, we have the following situations. First, the population variances sigma 1 squared and sigma 2 squared are unknown. Second, the sample sizes N1 and N2 are large, that is being at least 30, which allows us to use z-score in the confidence interval formula. And third, the unknown population variances sigma 1 squared and sigma 2 squared are assumed to be equal. So the two-sided 100 times 1 minus alpha % confidence interval for the difference between the unknown population means mu1 minus mu2 is given as follows. We start with x bar 1 minus x bar 2, which is the point estimate of mu1 minus mu2, plus minus the margin of error given by the product of z-score, which is z alpha over 2, and the estimated standard error of the sampling distribution of the difference between two means, given by the square root of SP squared over N1 plus SP squared over N2. Here, SP squared, as we knew earlier, is the weighted or pool variance used to estimate the unknown population variances sigma 1 squared and sigma 2 squared, which are assumed to be equal, in this case 2A. We can further simplify the confidence interval by writing it like this. By taking the square root of SP squared, we then have the margin of error equal to the product of z-score, that is z alpha over 2, the pool standard deviation SP and the square root of 1 over n1 plus 1 over n2. The pool standard deviation is given by this formula, which is the square root of the pool variance, where the formula for the pool variance is given in statistical table page 2. Now in case 2b, we have the following situations. First, the population variances sigma 1 squared and sigma 2 squared are unknown. Second, the sample sizes n1 and n2 are large. And third, the unknown population variances sigma 1 squared and sigma 2 squared are assumed to be unequal. So the two-sided 100 times 1 minus alpha % confidence interval for the difference between the population means mu1 minus mu2 is as follows. Again, we start with the point estimate of mu1 minus mu2, that is x bar 1 minus x bar 2, plus minus the margin of error defined by the product of z-score, which is z alpha over 2, and the estimated standard error of the sampling distribution of the difference between two means given by the square root of s1 squared over n1 plus s2 squared over n2. In this case, 2b, s1 squared and s2 squared are used to estimate the unknown population variances sigma 1 squared and sigma 2 squared respectively, where the two unknown population variances are assumed to be unequal. The next case is case 3a under category 3. In this case 3a, the situations are: first, the population variance sigma 1 squared and sigma 2 squared are unknown. Second, either the sample size n1 or n2 is small, or both n1 and n2 are small, that is less than 30. And third, the population variances sigma 1 squared and sigma 2 squared are assumed to be equal. First and second situations require us to use t-score instead of z-score in the confidence interval formula, whereas the third situation indicates that we should use a pool or weighted variance SP squared to estimate the unknown equal population variances sigma 1 squared and sigma 2 squared. The two-sided 100 times 1 minus alpha % confidence interval for the difference between two population means mu1 minus mu2 is then given by the following expression. Similar to the previous three cases, we start with the point estimate of mu1 minus mu2, that is the value of x bar 1 minus x bar 2, plus minus the margin of error, defined now as the product of t-score, that is t alpha over 2 nu, the pool standard deviation SP, and the square root of 1 over n1 plus 1 over n2. As we know, we changed the z-score with t-score because first, the population variances are unknown, and second, the sample sizes are small. Now, how do we have SP here? We can recall case 2a, where we had the same assumption on equality of population variances, and we used the pool variance SP squared to estimate sigma 1 squared and sigma 2 squared. By replacing or estimating these two unknown population variances with SP squared and take the square root of SP squared, then we have SP outside the square root, where SP is the pool standard deviation given by this formula. Now the next question is, what is the value of nu, which is the degrees of freedom for the t-score in this case? The answer is quite simple. Nu is simply the sum of nu1 and nu2, where nu1 is the degrees of freedom from sample 1 given by n1 minus 1, and nu2 is the degrees of freedom from sample 2 given by n2 minus 1. Therefore, nu equal to n1 plus n2 minus 2. Note that case 3a is actually similar to case 2a, but instead of using z-score, we now use a t-score in this case 3a. Remember, case 3a is similar to case 2a, but do not use z-score, instead use t-score in this case 3a. The other case under category 3 is case 3b, which is the last case out of 5 cases in this topic. In case 3b, we also have 3 situations. The first and the second situations are the same with situations 1 and 2 in case 3a, which require us to use a t-score again instead of using a z-score in the confidence interval formula. However, in the third situation, the population variances sigma 1 squared and sigma 2 squared are assumed to be unequal. This assumption of unequal population variances will affect the value of nu, which is the degrees of freedom for the t-score. Here, the 100 times 1 minus alpha % confidence interval for the difference between the unknown population means mu1 minus mu2 is then given as follows. As before, we start with the point estimate of mu1 minus mu2 given by x bar 1 minus x bar 2 value, plus minus the margin of error, now defined as the product of t-score given by t alpha over 2 nu and the estimated standard error of the sampling distribution of the difference between two means given by the square root of s1 squared over n1 plus s2 squared over n2. Since the unknown population variances sigma 1 squared and sigma 2 squared are assumed to be unequal, the degrees of freedom nu is not straightforward and simple anymore as in case 3a. The formula of nu is given below, which is provided in the statistical tables booklet, page 2. You are expected to get a real value for nu when you substitute all the required information such as the sample variances S1 squared and S2 squared and the sample sizes N1 and N2 in the formula. However, to get a value of T alpha over 2 nu from the statistical tables booklet, what you need to do first is to round the real value of nu to the nearest integer. Next, S1 squared and S2 squared are estimates of sigma 1 squared and sigma 2 squared respectively. Here, we do not use SP squared, which is the pool variance, because sigma 1 squared and sigma 2 squared are assumed to be unequal. Note that case 3b is similar to case 2b. Nonetheless, you should use a t-score that is T alpha over 2 nu, not a z-score in the confidence interval formula, in this case 3b. Having run through all the 5 cases, let us now explore a few examples on constructing the confidence interval for mu1 minus mu2. Let's go. For some examples and solutions on constructing the confidence interval for the difference between the two population means mu1 minus mu2. Please watch the next video I have prepared for you. Bye for now. Assalamualaikum and see you in the next video.